Todd Dunn here for Life on the Edge. This is my third video in my series on installing solar power in an RV. This video deals with wires, switches, circuit breakers, etc. I wanted to make this particular video because these components are often neglected in other presentations I've seen. I guarantee you that if you don't use wires, your solar system will not work. They're an essential component, so it's important to understand how to choose wires and how to make them the right size. Well, let's get started by looking at types of wires that you might use. Commonly, there are three types of wire available. One of the most common ones is single conductor bare copper wire. By bare, I don't mean that it's uninsulated. I mean that the wire itself is just copper with insulation over it. This is typical household wire. This wire is quite cheap. It's also pretty rigid or not very flexible. If you do flex it, for example by vibration, it will tend to break. It's also not a good choice for exterior use because the bare copper, if it does get wet, will corrode. Another common type of wire is stranded bare copper wire or automotive wire. In this case, the conductor is multiple strands of relatively small strands of copper wire that are twisted together to make the wire. This is moderate in cost. It's relatively flexible because of the larger number of strands, but again, because the copper is bare, it's subject to corrosion should it get wet. And finally, there's stranded tinned copper wire, which is also called marine wire. This is the most expensive. It is stranded just like automotive wire, but the individual strands are smaller, so there are more of them. This makes this the most flexible of these three wire types. I've put stranded tinned copper wire or marine wire in red because it is my choice for use in RV solar installations, particularly for the wiring that is outside the vehicle. It's going to get rained on, and if there are any leaks around the connectors, water will get into the wire, and because tinned copper wire is coated with solder, individual strands are coated with solder, it's much less likely to corrode. Now that we've decided what type of wire is best to use for the installation, we need to think about how big do the wires need to be for the different parts of the installation. First, I'm going to address the wiring from the solar panels to the solar controller. Just how big does that wire need to be? Well, wire size in any installation depends on three parameters: the voltage the wire is carrying, the amperage the wire is carrying, and the length of the wire run. Okay? Just in general, higher voltage lets you use smaller wires. Higher amperage, in contrast, requires larger wires. Now, fortunately, there's a simple formula to calculate exactly how big the wires need to be based on voltage, amperage, and the length of the wire run. Okay, I can tell you're all excited to find out exactly what that formula is. Well, here it is. The maximum length of a wire of a particular size is equal to 5 times the percentage acceptable voltage drop that occurs in the wire times the voltage divided by the product of the amperage that the wire is carrying and the resistance of the wire. This formula is based on the concept that any wire has a finite resistance. So if you put amperage through there, there will be a slight decrease in the voltage as the current flows through the wire. So we try to size our wires to minimize that decrease in voltage. Typically, for this sort of application, we use a 3% decrease in the voltage. So that defines the formula. Fortunately for you, I have already done all the calculations, and a good deal of the rest of this presentation is simply going to be showing you what those results look like. In addition, since I don't expect you to remember 4 or 5 slides of numbers. I have put all of the results of these calculations into my blog post, and the link for that blog is in the description for this video. The one piece of data that you're going to need to do these calculations is the resistance of the copper wire as a function of the size of the wire. I've calculated that on the basis of the number of ohms of resistance per 1,000 feet of wire, and this is the number that goes into the formula. You can see it varies from about 2.5 ohms for number 14 wire down to 0.15 ohms for number 2 wire. So that's just some data for the formula. The other numbers you're going to need are the voltage that your solar panel is operating at and the maximum amperage that the solar panel can put out. Okay, here's the first slide of results of calculations. I've done this for 4 scenarios, all assuming that a 3% voltage drop in the wires is acceptable. What this table shows is the maximum length of wire of a given size that can be used for each individual solar panel. So, for example, if you have a single 50-watt solar panel and your length of your wire run is 40 feet, you're going to have to use at least the number 12 wire. The table shows in the first set of data results for single panels of 50, 100, 160, and 260 watts. The next set of data is the results for 2 panels wired in parallel, again for 50, 100, 160, and 260 watts. These are the common panels that you're going to use. So all you have to do is look in this table, take the length of your wiring run, which is the length from where the wire is attached to the solar panels to the solar controller, look in the table and find the appropriate wire size based on the particular panel you're using, how the panels are wired, and the length of the run. Okay, here are the results for 2 panels wired together in series, and down at the bottom 4 panels wired together in series parallel. So these are all the common wiring configurations that you might use to get up to 4 panels together in your solar array. Again, this table is in my blog post, and the link to that blog post is in the description for this video. Now let's look at the wire size that's required to go from the controller to the batteries. This wire is different in size than the wire that comes from the panels to the controller because the solar power controller changes the voltage from whatever the panel voltage was down to the charging voltage. Normally, for this calculation, we would use the minimum charging voltage, which is around 13 volts, which is what I've done. As I'll show you, the results are different for PWM and MPPT controllers because MPPT controllers pass more amperage than PWM controllers do. When I modify the formula by putting in a fixed 13 volts, it becomes the maximum length of wire of a particular size is equal to 65 times the percent voltage drop that's acceptable, divided by the current or amperes in the wire and the resistance of the particular size wire. Here are the results for wire sizes going from the controller to the batteries. I've assumed a 1% voltage drop in this case because charging voltage is fairly critical in terms of getting the batteries to properly charge. At a 13 volts, 1% is 0.13 volts, which is not big enough to make a big difference. But if we went to 3%, we'd be close to half a volt, which is significant. Okay, the results are summarized here for single panels, 2 panels in parallel, or 2 panels in series. The results come out to be the same in those 2 cases. You'll notice if you look at these numbers quickly that the runs that are permissible for the different size of wires are much shorter than they were, if you remember the previous slides, for the wires from the panels to the controller. The reason for that is simple. First, the voltage is lower. You remember at the very beginning of my talk about wire size, I mentioned that as voltage goes up, the required wire size goes down. So conversely, if voltage goes down, wire size goes up. So you have to use larger runs of wire for any particular panel. Furthermore, the numbers here are pretty small, particularly when we get up to the higher output systems. This points out the necessity of putting your charge controller close to your batteries unless you want to buy a lot of really expensive wire. Here's the last set of results. These are for 4 panels in series parallel. You'll notice when we get up to the bigger panels, 400 watts of panels or 640 watts of panels, 4 160s, or a little over 1,000 watts, 4 260s, that even with the largest wires, the permissible wire runs are short. In other words, put the solar power controller close to the batteries if you have a big array, or be prepared to spend a lot of money on wire. Okay, this is the last slide in this presentation. And what I'd like to do now is just say a little bit about fuses, circuit breakers, and switches. First, circuit breakers are normally used to protect the wires, not components within the system. Fuses are used to protect individual components, such as your solar charge controller. Okay, let's look at a couple of things. When you size the fuse to protect your solar charge controller, you want to locate the fuse in the positive wire between the solar panels and the controllers. And if you have a 30 amp solar power controller, put in a 30 amp fuse. That will protect the controller from some fluke that causes a high amperage spike. If you're going to put a disconnect switch in, which I strongly recommend, it should be also located between the solar panels and the controllers, again in the positive wire and probably close to the controller where you've got things mounted. If you decide to use circuit breakers, they should be sized to protect the wire based on the rated amp capacity of the wire. I've got a little table over on the left for different wire sizes that shows the standard maximum amperage capacities for those wires. If you're using number 10 wires from the solar panels to the controller, you'll want to use a 30 amp circuit breaker. You would also then presumably put in a fuse after the circuit breaker to protect the controller, and that fuse would be rated less than the circuit breaker rating. However, oftentimes people don't use a circuit breaker simply because the fuse that's sitting in front of the controller in a properly set up system will always have a capacity less than the wire's rated capacity. So the fuse will blow before you get a current big enough to damage the wires. My recommendation for a typical RV installation would be to install a fuse and a cutoff switch so that you can disconnect the solar panel array from the controller to work on the rest of the system. Okay, that summarizes everything. I want to reiterate once again that the tables of numbers of the results of my calculations for individual solar panels wired in different configurations are all present in a blog post, and the link to that is in the description of this video. So if you want to get the actual numbers rather than try to pick them out after freezing this video at some spot, you can go to that blog post and read them right there. Much easier to do because they're not going to go away on you. Okay, thank you very much. I hope that you got something out of this presentation. I hope you have a better feel for the importance of making your wires the right size for your solar array. And if you liked it, please click the thumbs up button. If you didn't like it, go ahead and click thumbs down, but please post a comment and tell me why you didn't like it so that I can make my future videos better. And I would love it if you'd subscribe. Thank you very much.